Hi everyone, welcome to the second week of the summer school, and today we are finally getting into constructions of probabilistically checkable proofs, and we'll see the famous Hadamard PCP. And let's start just by reminding you what we've done last week. So last week we had focused primarily on property testing, on how to property testing and coding theory. What I mean by that, we looked at way of taking information and encoding it and endowing it with this like nice symmetry and nice properties, and building on that, we will now be able to get PCPs going on and to see constructions. I think there is a bit of echo, so if you're unmuted, if you're if you're not muted, please mute yourself unless you are asking a question. Okay, and this week, what we'll do is primarily two things. We'll see constructions of PCPs, and we'll get to see somehow the magic happening in stages. So today we'll see the first construction, where you can take an NP proof of your choice and be able to verify it using 3 queries, but the proof itself would be huge. So we're paying a huge price for that. And then you might say, oh, well, maybe just because we're dealing with this exponential size proof, then this magic of PCP can happen. But then over the next few days, we'll gradually improve the parameter, make things better. Let me just try to see if I can see thing myself. Just 1 second. This is okay. So I'm doing a mute all. Good. Okay. So yeah. So we'll gradually get better and better PCPs, and then we'll see how to get some really nice applications of that, both to complexity theory and also some practically relevant probabilistic and cryptographic proofs. So today we'll start by showing this exponential size PCP for NP, the Hadamard PCP. And essentially this is the theorem that we're going to prove. And okay, sorry for that. And let me kind of highlight the parameters. So we'll show that any language in NP, okay, any language in NP admits a PCP with perfect completeness. So that means that we'll accept every yes input with probability 1. We'll reject like bad input with probability half. So if you want a better success, you just repeat. The alphabet size would be binary. The length of the proof would be exponential. The number of queries would be O of 1. And the amount of randomness that we need will be polynomial. But I want you to kind of like, the main thing to take from that is these parts. So it's essentially a way in which we take an NP proof for whatever you'd like, for whatever language in NP. And if you allow yourself to encode it using an exponential amount of redundancy, then you'll be able to verify it just by making 3 queries. So think about like the purported proof that someone had that was up for the ABC conjecture, which took so many years, and even if you look at Fermat's death theorem, which took so many years to verify. So this means that if you're willing to present your proof in a very redundant way, then you don't have to go through all the steps and understand. It's enough to just like look at 3 bits of the proof, and then with high probability that you're correct, which is kind of a nice thing. Okay, so we'll see how this magic is happening. And just like to remind you again, like we're talking about the PCP system. So that means that we'll have this prover, and the prover will generate this exponential size proof, which will be written down. And we'll have this efficient verifier, which would probe it in, all of 1 locations, and then tell you whether the input is, like whether the answer is 0 or 1, using some randomness, some polynomial randomness. Okay. So So the sumness is 1/2, but think about it, it could be like 1/1,000,000, and we just like, it would still be a constant number of queries. So now let's see what the proof strategy. It would be a proof in 3 steps, one of which we've already done. So, and remember that the trick is indeed that we already can build on these nice ideas that we saw in coding theory, where we solved, for example, here the Hadamard code, and that we can actually test it. And I'll remind you all of that. So here are the steps. So first of all, we will construct something which is called a linear PCP. So what is a linear PCP? A linear PCP is a PCP that has nice linear structure which enables this local to global phenomenon. And what does it mean? It means that we know that whatever the proof that the verifier, that the prover is providing us, the PCP proof would be a linear function. And it means that we know it's a perfect linear function, and we know that even a malicious prover must send a linear function. We'll see in a second, like the model, but the idea is that, we'll design a PCP under the assumption that we have this nice linear structure. And then we'll have a linearity test, which we've already done in lecture 2 last week. And using that, we can combine the linear PCP with the linearity test to get an actual PCP which doesn't have this dependency on linear structure. And as you can imagine, what we'll do is, in fact, the actual PCP will start with this test that will show us that, in fact, we are really close to be a linear function, and we'll use some source correction. So in some sense, using the testing, the linearity testing algorithm, we'll be able to assume almost without loss of generality that everything that is being sent is linear, and therefore we have lots of nice structure. For example, if I want to read a point, I can choose a triangle x, y, x plus y, and correct the value of x at points x and y. But you'll see all of that in a few minutes. So I want to start with not exactly a reminder, but rather reframing what we've already done in terms of the Hadamard code. So, we said that a function over a finite field in n variable is linear, right? If you can just write it as a linear combination of its variables. And, we've looked at the subset of linear functions as with respect to the subset of all possible functions. And we saw that this is a subset which is of the number of linear functions is it's a subset which is logarithmic in the size of all possible functions. It's a highly structured subset. And in fact, if we look just at the subspace ling, which consists of all functions which are linear, this is the Hadamard code. The Hadamard code is defined to be the truth table of all linear functions defined over some finite field. But this doesn't tell us how one encode a message using the Hadamard code, right? I mean, what we want to do is we want to start with some empty language, maybe 3 coloring, maybe 3 sat, and we want to kind of make it, encode it into a Hadamard code word. So for that, how do we start with just, some bits of information and encode it into a linear code word? Does anyone have a suggestion? How can I, suppose I'm giving you this, x in f to the m, and now I'm asking you associate it with a linear function. Any suggestions?
Coefficient CI.
So okay, so that's a very good way of doing it, and we'll use something which is slightly different, in some sense equivalent. You'll see exactly what I mean. So it's more like taking inspiration from the degenerate case of the Ritz representation theorem in functional analysis. We'll do it using just explicitly writing the inner product function. So what do I mean by that? So I'm getting this x, and I'm saying, how would I associate it with a function f of x? So what I do is I just define the function which, given some vector in Fn, Z, just returns the inner product of X and Z. Now, of course, this is nothing other than just summing over Xi, Zi. So it's exactly what Wilfred said. It's just like just being done in a slightly more explicit way. And then, in fact, it's completely equivalent. I take it back. So that's what we'll do. And in some sense, this is how we'll think about linear functions. So, if you want to cover any linear function, you just take the inner product, the function which returns the inner product with a certain vector of your choice. And so now if I want to take, my favorite, suppose I want to take some coloring of a graph or a three-set assignment, I can just use it to define a function f of x, which would return all possible linear combinations. And we'll see that this innocent change of perspective would lead us to something really nice. Okay, so any questions regarding the Hadamard code?
I have a question. So,
yes, please.
So here you are referring, so code word, the way we interpret a code word is something which is data, not a function. But here you are interpreting code words as functions. So can you clarify?
Yes, absolutely. That's a very good question. And just sloppiness on my side. When I'm saying a code word, I mean the evaluation of a function over its entire domain. So what would be, and this would also explain the size. So, I'm starting with this, vector of n field elements in F. Using this vector, I am constructing a function. And this function is exactly, the function that I mentioned. Now, I started with x, and now I got the code word f of x. So what is f of x? I take this function f of x, and I evaluate it over all possible z's. How many z's are they? So each z is also an element of f to the n, so it's of size f to the n. Right? So I took a linear function which can be represented using f of n elements just via its coefficients, and then I evaluated it over the entire domain, and so I had the truth table of a complete function. So this is the size of the representation. And this is exactly why this encoding is extremely redundant, because we are writing an exponential truth table of a function which we can actually represent by just writing by an n-dimensional vector. Does this make sense?
Yes. So in order to change the code word, we'll have to change the message, right? We cannot change the inputs to the function. The input to the function, the parameter x defines what the code word is. Is that correct?
Yeah, so I take a message x, and then I consider the function f of x. I write down as a huge vector all of its evaluations, and that's the code.
Got it. Okay, thanks.
Good, thank you. Okay, so that's the Hadamard code, and it naturally leads to this notion of a linear PCP. And what would be a linear PCP? Essentially, it's a PCP in which we are guaranteed that the proof is a linear function. The proof is Hadamard code word. So we'll have these two conditions. One is that the honest proof is indeed a linear function. And the second one is that even if we are on the soundness, even if we need to kind of deal with cheating verifiers, then we can assume that they only send linear functions. And later we'll use linearity testing to enforce that. But for now, we take it for granted. And that's a linear PCP. I should mention as an aside that in addition to being, this intermediate notion, which would clean up the analysis and would allow us to, decouple the testing part from the PCP part, this is also a massively useful notion in practice, and there are actually linear PCPs which are implemented in practice, and you'll see exactly why this could be helpful. So again, we'll use this perspective of associating a linear function with an inner product. Again, we'll have, suppose rather than saying that the proof is this exponential size evaluation of a function, we'll say that the proof is this collection of elements to which we can consider the inner product of this proof with each point. So let me maybe show a diagram which would make it a bit easier. Here is a different perspective for the same thing. So I can tell you, what is a proof for a linear PCP? It's an exponential size evaluation of a function. Alternatively, you can think about the proof as being, just a concise representation, just a list of coefficients. That's this pi here. And then the prover can ask for any linear combination of this vector. Okay, so I'm going to say it again, because even though it's completely trivial, it's a confusing point. So I have two options. And it's the same thing, just a different perspective. One perspective is I can write down the PCP as it is. So this would be pi at 1, pi at the second point, until pi at the, f to the L point. So the exponential many places. Alternatively, and so this is not pi, this will all be f of pi, sorry. F of pi, f of pi, and f of pi. And alternative ways, I could say, well, think about it as the proof being just this pi here, and then each query just specify, I want this elements times 3, and plus this elements times 2, plus this element plus 0, and return the value. Okay? Does this make sense? If there are any questions regarding that, please let me know.
So one question. So here we are thinking of the proof pi as the message, and then the responses to the verifier as bits of the code word. Is that correct?
As linear combination of the code, of elements of the code words. Yeah. Like the message is pi, and rather than being able to query pi, we want to be able to kind of like say, maybe I want to take the sum of everything. Or, 1 plus the first element, plus 3 times the second element, plus, something like that. And the cool thing about the Hadamard code is that if you have the Hadamard encoding of pi, then you can make one query and get any linear combination of your choice. That's exactly what a linear function here means. Because, we said that any linear function can be expressed as an inner product. And then it means that we can look at any point and get any linear combination of our choice. So this is something which is, if you sit down for a few minutes and just stare at it, it would become evident that it's completely definitionally trivial. But I have to admit that for me, it took a while. It's a bit confusing because there are 3 perspectives. You have the code word perspective, you have the linear function perspective, and you have the inner product perspective. So just take a bit of time to digest, and this is why I'm doing it so slowly, and I'll keep reminding you that. But it's actually all the same thing, just different perspectives. Okay, so the formal definition of an LPCP or linear PCP would just be what you expect. If you have a X in the language, if we have a 3-colorable graph, then there exists some proof, some coloring, coded coloring, such that we will accept with high probability. And otherwise, any proof we will reject. We will only accept a false proof with a tiny probability. And the key thing to notice here is that we are assuming here and here that we can access an actual linear function. So it cannot be the case that that the function which is written there is noisy or not a linear function. It must be a linear function. Okay. So that's what we'll do, and we'll have the same notation that we have for classes of PCPs, only we'll add L, and this would mean that we can assume that everything is, that everything is linear. Okay, so let me know if there are any questions. And so the theorem that we'll prove would be the exact theorem that I stated before, almost exactly. And we'll see, using length, which is n squared, and this is not really n squared, it's n squared, in the sense n squared like that. It's n squared assuming that you can make any linear combination. So if you actually want to write it, it would be exponential to that. That's the only thing which is different. So what we'll see is how to take this type of object as we defined, and using a proof, which is a linear proof of size n squared, we can make just O of 1 queries in order to check it. Okay, so, and then later we'll show that every LPCP can be transformed into a standard PCP. So these are the two things that we're going to do today. And each one of them will take us roughly 30 minutes.
I have a question. So
yes.
Why are we changing the definition of the length of a proof? So earlier we defined the length as proof as consisting of a sequence of symbols and then a verifier accessing any particular symbol. And now here we are changing the definition of length by saying that verifier can take any linear combination.
So just to say, the reason is out of like convenience of enforcing linearity. So what do I mean by that? Just to kind of, at the risk of confusing, but what I'm saying is that, we want to, you can have a definition that will be perfectly valid in which you're getting, some proof, which is what I drawn here in blue, where you have the guarantee that this is a Hadamard code word. That's a completely valid definition, but it would be convenient to us to think of the proof as some arbitrary information, which is not encoded, but we're just being able to query linear combinations of it. And the reason why this is the same is because if I want to query, so here the prover can do whatever it wants. It can send here, there's no restrictions, but I'm able to query, using one query, I can check any linear combination. And how do I do that? So suppose I want to, look at some linear combination X inner product pi, I can just look at the Hadamard place, which corresponds to that. Does this make sense?
Yes. So this length is actually a length of the linear PCP and not the actual PCP.
Yes, it's the length of the linear PCP. Exactly.
Okay.
Good. And again, I'm kind of like encourage you to go over this, after the lecture. You'll see it's trivial, but it is confusing. I definitely won't lie. So now let's start to do something which is, a complexity theory 101, like a classic result from the, prehistoric times. And we'll show that quadratic equations are NP-complete. Right? It's kind of a funny thing because it tells us something about the importance of linear algebra. So 1 minute aside of interlude of something that I once heard from one of my professors, that in some sense math consists of two things: linear algebra and our attempts of reducing the complexity of the world and reality into linear algebra. So, you look at analysis and we look at the derivative. So what is a derivative? It's a way of getting, well, the world is not, linear, but here's an approximation, a linear approximation of that. And this extends, I kind of challenge you to come up with natural examples of major fields where what is not happening is trying to reduce it into linear algebra or some basic combinatorics. My theory of that is that as human beings, we have a good understanding of linear structure and of combinatorial structure. But when we get into the quadratic realm, when we get beyond linear, then things are hard. And I think that this notion of linear equations that can be solved in P and quadratic equations that are NP-complete kind of give us some evidence to that intuition, right? Because solving linear things is in P, so it's also what we can do as humans. But yeah, the moment that you add these non-linear terms, everything gets complicated. Okay, so me /end philosophy, And let's show that quadratic equations, it's in fact in NP, it's an NP complete problem. So what is the problem of solving quadratic equations? You get a bunch, let's say m different quadratic equations. So maybe, you have this, I don't know, x1 times x squared, just like terms with each monomial is at most of degree 2, and this is total degree. So this is like, yeah, so you can't have, x squared, y squared. And you want to solve all of them together. Maybe here with everything that is being equal to 0. Right? I mean, if you come from algebraic geometry, then this is an algebraic variety, but we'll make no, attempt to talk about this geometry here. We just want to show that this is NP complete. And the reason why this is NP complete is kind of a simple thing. Well, we can start with the problem of Boolean circuit satisfiability. Right? This is an NP complete problem. You can also start from, from 3-stat or your favorite thing, but this is a bit nice because you say, it captures any Boolean circuit. And what we can do is we can take the wires of this circuit and just give it a name. So we have, like the inputs, and we have this internal computation and some output. And now what we can do is we can take equations to enforce gates, right? So I can take this equation, which, for example, we have the NAND gate, which is like a complete gate for a universal gate set. And we can use it, we can just like write some low degree polynomials. It's just like simply quadratic equation, not even low degree, it's this quadratic equation which gets the NAND gate. So for example, just another way of putting it, take any, Boolean circuit, and it's NP complete to know whether it's satisfiable or not. So what you can do is you can just like write it algebraically as a bunch of quadratic equations, just because you can go over the circuit and maybe you had a circuit and the circuit is like, you have an OR gate and here you have an AND gate. So each one of these gates, and then you have a NOT gate. Okay, NOT gate should not look like that. This could be another OR gate. But you just like algebraize, you write the circuit as an algebraic formula, and then you just check that you satisfy all of these conditions. Okay? And the only thing which is missing here is to enforce Booleanity, because it's a Boolean circuit. So you don't want to be able to write, something which is completely 7. That would kind of fool our. So the way we do it, we add this additional constraint, which say that x times 1 minus x must be 0. And this equation only holds if x takes the values 0s and 1. Okay, so it's a classical thing. You can see it in the complexity book or Barak in like, I don't know, maybe the first chapter. Nothing, really deep, but yeah. And now we want to take this particular problem and show a linear PCP for that problem. For the problem of solving, before that. So what we want to do is to show a linear PCP for this problem, but as a warm-up, we'll first focus on the linear case, right? So, we want to do it with respect to degree 2, but let's start with degree 1 first, right? And then we'll build into degree 2. So now recall this is a problem in P, so it's not a hard problem, but still, let's see if we can design a linear PCP to deal with linear equations. Okay, so what do I have here? So what is our setting? You can think about some matrix M representing, a bunch of linear equations row by row, and we'll have this vector B and vector C, and essentially what we want to check is whether C is equal to MB, right? This is just like M being a bunch of linear equations in the vector B, and we want to check this condition, and now we're augmented with this like nice power that we can take, linear combinations of the elements in B. So maybe just like to make it slightly easier to parse. So I have this M here, and I have this, oh, I think actually I wasn't lazy and I thrown it. Or maybe I did, I wasn't, never mind. Okay. So yeah, so we have just like this picture, so we can kind of remember we have M, these are all of our linear equations. This is B, and we want to check whether this is C. Okay, so I know I kind of like already displayed this on the slide, but in case you didn't see, any thoughts on how one can, like, what would be an idea to check such a condition? Like, how can we check this? So, I mean, the naive thing would be, you know, just query everything and check each one of the constraints. So, you know, you have some linear equation, x1 plus x7 equals 0. So go and check it. But that would cost a lot. We'll have to query the whole thing. So how can we save on the query complexity? Any suggestions? And also with respect to Tal's question, we do assume fanning of at most 2, which is still complete, yes, in the previous slide. Okay, so let me tell you my idea here. Like this, like the, not my idea, but like the, you know, the generic idea. And yes. Exactly as was suggested by in the chat by Hila and Arensena, which I hope I pronounced your name sort of correctly. Sorry if not. The idea would be to use this random linear combination, which is exactly what we've done in Fry. So it's a recurring thing. You'll see this recurring thing when we want to solve a problem, and there are many, you know, instances. So we kind of combine them to reduce the amount of work that we're doing. So, I remember that I wasn't lazy and I've thrown something. So what we want to do is the following thing. So we think about this matrix here, and we say, I want to check this condition, and this condition, and this condition, and this. I want to check that all of these things are equal. So instead of going one by one and checking all of these n conditions, maybe I want to just like sum them all together. So, you know, suppose that for simplicity, think about C being equal to 0. So we want that every matrix multiplication here by a vector would be 0, 0, 0, 0, 0. So one natural thing to do would be just sum all of these things together and check that the sum is still 0. But then you might say, oh, well, maybe what happens if we have some cancellations and things like that, exactly as we have with prime. So you put some random coefficients and you multiply it by a random thing, and so you argue easily that, you know, without, unless you are extremely unfortunate in your choice of randomness, then this would only equal C if all of the constraints are being satisfied. So here is the idea being written more formally, and it might look a bit off-putting when we first just like look at it, but then when we see the completeness, then you'll see exactly why it's defined this way. So what would the verifier do? We'll sample some random field element, we'll query B at this M transpose time R, and this is all this is doing is exactly that. It's just, you know, solving this linear equation, like taking these equations plus R1 times these equations, R2 times this equation, and so on, combining it, and checking that the inner product of C and R is the same as the inner product of B and Q. So notice that B and Q, this is just like linear query to the B string. And C of R, we can do by ourselves because we're holding it. It's not something that we need to query. So let me show you exactly why this holds. So, and this would make it much clearer, I promise. So suppose that we are getting, that it really is the case that B is a satisfying assignment, that M times B is equal to C. So if this is the case, then what do we know? So for any random combination that we choose, it doesn't really matter, all of the equations are being satisfied, we'll have that the inner product of C and R is exactly the same as the inner product of MB and R, just because C is equal to MB, right? So it's just like putting this. And now I can just like always change the order of a linear product by transposing the matrix. So this is just the simple identity. And that is exactly how, this is exactly B times Q, because that's the exactly the way that we defined this combination, right? So in fact, we have immediately, like we check that this condition holds. And now what happens in terms of soundness? Well, suppose that C is not equal to MB, then what would happen? It's the following thing. Well, you may ask, what is the probability that these two inner products would coincide? Well, we are doing the same step as we did here, just like writing, we want to say, oops, sorry, what is the probability that C of R would be the same as B of M transpose R? And then we can say, well, what we can do, it's a linear product, it's an inner product, so it is a bilinear function, so we can just like rearrange it and write it as this in this way, just purely manipulating the terms and rearranging. But now notice what happened. So we can just write everything. We can explicitly write the inner product, right? So this is like an inner product. It's like sum over I of this term times this term. Now we are getting here a polynomial, right? This is a polynomial. And the nice thing about the polynomial identity testing is it tells you that the probability that, you know, that a random point of a polynomial would be a root is exactly 1 over f, which is just the polynomial identity testing lemma, right? Just like, you know, so we just fixed our polynomial to be this particular function. And then we know that, you know, only like the polynomial that would take a value 0 only with that probability. And then we're done. So it's, you know, fairly notationally heavy, but it's a fairly simple idea as well, I think. Any questions regarding what happened here?
I have a question. So, so verifier is querying L bits of information, right? So the communication complexity of the verifier here is L. So I don't see why can't it just read all the L symbols from the proof directly instead of?
Sorry. No, so this is a bit confusing regarding linear PCP, but think about it as just one query, because later we will emulate this thing. It would be just by a single query. So all the verifier has to do is to specify a location P, which is a location Q, sorry, which is, you know, some vector of linear length. And in order to, so you have to specify this many elements, and then you get the value at this location. This is very different from taking this matrix, which corresponds, you know, to this massive amount of information. So it is, in fact, yeah, just like it's a very concise representation. But I guess that this would make much more sense once you see how this unpacks into a real PCP, where the encode is this kind of exponential. This is just a single query here.
Yeah, the query is, it's just a single query, but the communication cost of the verifier.
But there is no communication, remember, like the prover wrote down a proof, and then we're not communicating anything. We're just choosing which location. So this is, you know, we can say that we're using a certain amount of, you know, memory in order to find this location. But like, think about that, like somebody wrote down, you know, on some huge file, this information, then we're choosing, B is just the index that we choose to read, right? We're not sending this information to a prover, which then corresponds with something. We just pick a location on something that has been written on a piece of paper.
Right, but the size of Q is L, right? L
Sorry?
the size of the query queue is L symbols?
Yes, it is. It's the same as the size of B.
Right. Okay.
Okay, thank you. Okay, so that's the linear trick. Now I want to kind of like ask, how can we go from linear to quadratic, right? So let me kind of explicitly put the problem that we have. Like, we know that if everything was linear, we can just, in a sense, take, if there's a bunch of constraints and things we want to check, so just take a random linear combination of these and problems, merge them into a single problem and check it, just fold it. But, well, we have these quadratic terms. So any idea how we might be able to deal with quadratic terms as well? Okay, wow. So fantastic answers in the chat. I think maybe I should let you lead the discussion. No, excellent. This is exactly what we do. So let me just like say it. I mean, so we had this polynomial, and we know how to deal with these terms, but we also have this, quadratic terms that we don't know how to deal with. So one thing that we can do is maybe ask the prover to just give us the value of all monomials of degree 2, right? So think about the prover providing us with a new variable, an auxiliary variable, zij, which is equal to ixi times xj, right? So here, what I'll be able to do is to say, well, the prover kindly provided here this z1, 2, and this z of 2, 3, and z of 1, 3, z of 1, 1, and so on and so forth. And now this is, again, a linear function, right? It's a linear equation in the new variables, in the x variables and the z variables. And we reduce the problems and we're all happy and all is well. So what's missing? Why this is not enough? Why can't just like the prover, give me these values and just say, do the previous protocol? One thing which is missing.
The prover can lie in the, like, if he gives a zij, it doesn't have to be consistent with some other zik, for example. Like,
exactly. So as Jackie said, and Wilfred and Ila, overwhelmingly, the problem is consistency. And you'll see that this is a recurring thing. We have a prover, it is untrusted, and we need to check that this whole structure is being preserved, right? The key word is how to check consistency between linear and quadratic terms. Because, we could kind of like say, yes, this is z of 1, 2, and plug in whatever values that would convince me, but in fact, this is not at all what is claimed here. So how do we deal with such pesky provers? So what we'll do is we'll do this trick of using tensor structure, which will be super compatible with what we've done. We need to do minimal technical changes and things would work nicely. So now let me remind you. So what is the tensor product of two vectors in Fn? So you take a vector and you multiply each one of its entries. You kind of like replace it by the vector multiplied by a term. So if you think about what happened when you take this A and you take its tensor product, then you get an n by n matrix whose ijth element is exactly ai times aj, right? So this is like a nice, concise way of saying, suppose I want the prover to send me these all of these zij's. All it has to do is to send the tensor product of x with itself, right? Just the tensor product. And we'll have this notation just because we want to compare this, these terms. We'd like to think about them as a vector and not as a matrix. So we'll denote by flat of this tensor product, just flattening the matrix into a vector, right? So I have this like matrix, and then I stack all of these vectors one after the other. all of the rows, one after the other. So this is simple, and then I can compare them to vectors. I can take products of them and do things of this sort. Any questions regarding the strategy that we're going to do over the next 5 minutes or so?
I have a question. So there was a problem with the first approach, right? In regarding the consistency check between different z variables, but I'm wondering why can't the verifier introduce additional checks to check for consistency?
So this is exactly what we'll do. And we'll kind of like use the tensor structure to do it in an efficient way, which is kind of like compatible with this whole take random linear combination of rows of the matrices and stuff like that. In a sense, what's really happening is that we'll have the prover specifying all of the linear terms, specifying all of the quadratic terms, and then we'll check that really this matrix of all quadratic terms is indeed consistent with the linear terms, and then run the whole thing. The whole tensor structure would just enable us to do it in a convenient and an efficient way.
Okay, got it. Thanks.
Okay, so let's try to do the tensor structure. So what's the problem here? It's exactly what we discussed so far. We have a verifier, and the verifier has these linear terms, right? So we can make these linear queries to the linear term. So this is the short vector of linear terms. We have the long vector of quadratic terms, all of the monomials. Think about it as B being, this tensor of AI. So this is like, x1, x2, x3, x4, and this is x1, 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 x2, and so forth and so on. And the goal that we'll have here is just to check, is this B vector the tensor product of A with itself? But because I want to kind of like write equality, and this is a matrix and this is a vector, then I just like write it according to some pre-agreed way of ordering the rows one by one. So that's a problem that we want to solve. And assuming we have that, then we can kind of, solve the entire problem. So here's the idea. And again, it looks confusing when you just see it, but then when we go through the completeness, we'll see why things are defined the way they are. So what we'll do is we'll sample these S and T, two field elements, and we'll query the quadratic terms vector at this tensor product of S and T being flattened. So think about this as a way of doing a random linear combination with respect to a tensor, right? So I want to kind of like, do a random linear combination to a tensor. So what do? How do I do it? I take two random elements and I tensor them and flatten them just so it would be a vector. And then I'll query this A at the point S and at the point T. And I'm checking this condition, right? So querying A at point S means getting the value A inner product S. And querying A at point T means getting this value. So all I'm doing is I'm making one query, two query. So I have these two queries to A, and I have this one query to B, which is a random linear combination, and I check that it's the same. So it is notationally confusing, but in fact, it's exactly what we've done before, only with tensor structure. So now let's see why this holds. So assume that completeness, that B really is the tensor product of A with itself. So B really consists of all of the monomials of degree 2. So what happens? I'm looking at F at B inner product with the flat of S and T. Definitionally, because B equals to A tensor A, it's just like flattening of A tensor A and the flat of S tensor T. And now I take this whole thing and I write it explicitly as an equation, right? So, it's summation of these terms times these terms. So I just get this summation of I and j of ai times aj times si times tj, right? Just like literally taking the definition and writing it down. And then I can group it according to a linear combination in S, and group it according to a linear combination in T, which is exactly what I'm getting. So, this is just like the way of, we just check a random linear combination in these terms. And now for soundness, we'll do exactly what we've done before. So what do I mean by that? We'll assume that B is not really the set of all monomials. So there is at least like one monomial which is inconsistent. And that's kind of like even let it have a name. So, maybe let's say that the monomial which corresponds to, xi times xj, xi star times xj star is actually not, it's like the B that we have is not really, doesn't really take this value. So suppose we have that case. Well, what is the probability that the check will fail, that we will see that these two things are disagreeing? Well, we can just take this whole thing and write it down explicitly, as we did here, and group it in this way. So at this point, so this is, it might look confusing, but this is just rearranging, like writing down the definition of an inner product and regrouping. Just simple algebra. And why do I do it this way? Because now I'm getting this polynomial, and now I can apply the polynomial identity testing and say, well, as before, this is a polynomial, it has a certain degree, and so the probability that of soundness, the probability that this would be equal is small. But in fact, I want to do something slightly more complicated, just so we'll get better parameters, and we'll want to invoke the polynomial lemma twice. So let me show you exactly what I'm doing. By the way, it's not crucial. It's only crucial if we want this also to hold for F2. But let's do it for the sake of it. It's just like a minute. So first, what I'm doing here is I'm taking the sum and I'm breaking it into two sums. This is fairly harmless. And I'm saying, well, let's take all of these terms which correspond to T and just write them. They constitute some polynomial. So what happened is I took this polynomial that I wanted to check to begin with in S and T. And what I'm doing is I'm dividing it to a polynomial in T and a polynomial in S. And what this allows me to do is kind of like a two-step procedure. So first of all, I have this polynomial P in T. And then after I evaluate it, then these are actually can be viewed as the coefficient of another polynomial in S. Right, so I have this like I have like the T variable and the S variable. And so what I'm doing, I'm decoupling them and I'm using one of them to be the coefficients of the other. And why do I do this thing? Because then I can say that the probability that, this whole expression is not equal to 0 is just a probability that there exists one location, one point I, such that Pi of T is not 0 and Pi of T at S is not 0. So these are these two independent events, right? In one of them, and then all I can do is to say I just apply the polynomial identity testing, the PAT problem twice. So this means that it all works with probability. The failure probability is 1 over F. So here the success probability is F minus 1 over F, and I apply it twice, so I get these things squared. So the moral thing, the important thing to take of that is that you can look at this thing, it's just a polynomial and apply the polynomial identity testing, but one can be a little bit more clever and get slightly better soundness of this form. Okay, so let me answer some of the questions in the chat. So is it enough to query A on R, B on the tensor for only a single R? Yes. So we'll just take, as we did in the linear case, we just take a single random linear combination. And there's a question regarding why we assume a place where, so why do we assume that there is, okay, I think, why do we assume that? So Bogdan, can you clarify your question?
Yes, so if I understand correctly, we start with an arbitrary quadratic polynomial, right? Arbitrary
yes.
Quadratic polynomial, which means that we have basically like n square coefficients.
Yes.
Okay, so if you take a random one, like say like Kolmogorov complexity would be about n square, right? But then if we can choose a of length n such that b is expressible through this a, then it's sort of a contradiction because the complexity of this a would be at most like 2n whatever. So I think can make sense.
Yeah, I guess what is happening is like, first notice that the first thing is that I'm saying, well, here we're not looking like we'll soon in the next slide we'll kind of see how to deal with quadratic equations in the general form. But here what I'm saying is I'm taking this vector A, and I'm then looking at the purported tensor product of A with itself. So what is A tensor with itself? It's a matrix whose entries are, you know, A1, 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 A2, A1, A3, until AN, AN. And all I want to check is that these two things are consistent.
Okay, so we are checking basically that our quadratic polynomial is something very specific.
Exactly of this tensor form, yes.
Okay. Thank you.
It is asking regarding the provers, so whether so in the completeness, we assume that they are honest, and in the soundness, we assume that they can be malicious. However, they must still send a linear function. They must like still, we still can make these linear type of queries, and to go regarding the soundness error in terms of f again. So just to say, as you saw, maybe it would be easier to see it again in the previous slide. So in the previous slide, we had, you know, what is the probability of, let's see if I can play. Okay, yeah. So right, we kind of like said that we apply the polynomial identity testing, and then the probability that the random place would kind of get, would be 0 is 1 over f. That's just the polynomial identity testing. So now we do the same thing in the quadratic set, in the tensor structure. And what is happening here is that we're saying that I want this condition, I want these two conditions to happen. So these are two PIT problems. Each one of them will fail with probability, you know, will succeed with probability the inverse of that. It's like always the union bound one has to be careful. So, you know, the probability of the good event is, of the bad event is 1 over f. The probability of the good event is 1 minus that. So it's f minus 1 over f. And then I have these like two independent events. So they are squared. So it's just the thing, and it's kind of like, you know, it's the same type of, the probability that in one day it would rain is half. So what is the probability, is maybe, you know, if the probability that it would rain in one day a third, so what is the probability that it would rain in 2 days? So it's not a union, but it's not like a third plus a third, but rather it's, you take the complement and you multiply. So that's just that trick.
Okay. Can you explain the first equality in the last line again? Sorry.
First equality in the
last line.
Yeah. So you mean how to go from here?
From here, yeah.
To here. Yeah. Okay.
Yeah.
So we want this, we want this polynomial to not be 0. And I want to say, when would that not be 0? Oh, so I see what you're saying. Yeah, so what I'm missing, this should be probably an inequality, but we'll see in a second. So I'm saying that a sufficient condition for that is that there would be one place where both of these are. Yeah, okay, I see that. You're absolutely right. It should be, yeah, I keep doing it in soundness analysis, but I'm thinking in terms of flow bound, and I write equalities. Yeah, so this is like one sufficient condition. Thank you.
Yeah, that makes sense.
Also, these polynomials in the last line, the PIT, are not on the same t's, right? They can have different t's when instantiated.
So I'm not sure what you mean. I mean, like they are completely different polynomials formally, and they're being evaluated. But like it just happens that they'll like they both are defined, like over f to the n. So I'm not sure what you're asking here.
Polynomials, but what I'm saying is that in the previous summation, the double summation, all the t's were different t's. But when you write it as a single summation, you implicitly assume that all the t's for the SI coefficients are same. The polynomials are all evaluated on the same t.
Wait a minute. Let me see what you're saying. So I am summing over I, and I have n different polynomials, and
all being evaluated on the same point. Is that correct?
All evaluated on the same point. Yes.
But that is not what your double summation says.
No. So let me see. Okay, I'm writing here these two polynomials, and then what am I grouping? I'm just like, what is my PI? I just take this chunk of thing and I call it PI, and then I group it and I have it with respect. Yeah, so I have these various PIs, each one of them being applied with respect to these t. So this whole kind of thing becomes my polynomial. Does this make sense?
Okay, yes.
And also, if you want, I can like let's stay after the lecture. I can write it down in more steps and make it even. I can try to make it clearer. But thank you. Okay, so now we want to take these two things and make them and create a linear PCP for quadratic equations. And I can only say that like we're essentially already done. Like why we're done? Because we have the tensor structure, which allows us to deal with these quadratic terms as if they were linear terms. We have another variable. We can check that everything is consistent. And so all we need to do is like do the first thing, the first linear protocol, but also with respect to the auxiliary variables that we had. So, this is what we're going to show. We're going to show, for the quadratic equation problem, we're going to show this linear PCP. And again, the parameters are always as always, but we'll have a proof here, which will consist of the quadratic terms and the linear terms. I don't know why the arrows in different directions. And we'll only make 4 queries here. Right, and the amount of randomness you see, that it's just like the natural thing. So, we start with this bunch of polynomials, and we'll have a verifier which requires this proof, which will get this proof over Fn plus n squared, right? So it's, by the way, this is something that I should have mentioned before. So let me just like make, we had this discussion, and I kind of thrown this verifier, and it has a linear PCP, like it can make linear queries to A, and it can also make linear queries to B. So this model has 2 oracles. So you might ask, is that a linear PCP? I mean, how can I deal like with these 2 different, like syntactically, I only said that there is 1 oracle. But the point is that you can always stack this A and B as 1 oracle, just the concatenation of it. And then if you can do any random linear combination, in particular, I can take a random linear, any linear combination, you can take a linear combination which completely ignores A and completely ignores B. So just, so this is exactly what we do here. We just like write down a proof, which is concatenation of all of the linear terms and all of the quadratic terms, and we can treat it as two separate proofs if we'd like, or as one. Okay, so now what is the verifier? What will it do? So first we will sample one field element for the random linear combination of the linear equations, and we'll sample this S and T, two field elements, for the random linear combination of the tensor. So exactly what we need for test 1 and what we need for test 2. And then we'll consider this matrix M. And what is this matrix M? Think about it as having M row vectors, each row vector representing one of the M equations that we're trying to solve, P1 to Pm. But this vector now, this is the confusing part, so let me say slowly. Each vector will consist of all of the linear terms, you know, this like x1, x2, x3, and this would be the first n locations. And starting the n squared location, it consists of, you know, x1 squared, x1, x2, and so on and so forth. So I'm just like taking a vector which consists of all of the like terms of degree 1 concatenated with all of the terms of degree 2. And then I can write the whole problem as a linear equation in all of these terms. And as always, I already prepared something, but then I forget. Okay. Yeah, so this says that. Okay, and then what we're going to do is we'll make queries to, you know, the concatenation and AFP. So we'll make to both of them. So we'll take the random linear combination that we needed with respect to the linear equations, but with respect to this entire thing. And we'll also do this consistency test by querying B at a random linear combination and A at a random linear combination. And we'll check these exact two conditions, that the linear equation in the linear terms and quadratic terms, so that these things hold with respect to the constant. So this is just checking this is the first test that we had for linear terms, only now we augmented it with variables for the quadratic terms. And also the consistency check that we need to check the tensor structure to make sure that the quadratic terms are indeed, you know, got there to be a tensor of the linear term. So it's indeed, you know, there is consistency. And now, you know, completeness and soundness will follow in the straightforward way. So completeness, if everything is kosher, everything is good, then, you know, we have these polynomials, all of them are satisfiable by this A, and we're setting B to be the tensor of this satisfying assignment, and then the tensor check will pass with probability 1 because it is a tensor, and the linear check will pass with probability 1 between this is actually a satisfying assignment for this system. So this is simple. And soundness, well, you know, if this set of equations have no solution, so any proof that you give, any, you know, assignment, so either it won't pass, either we're cheating and the prover doesn't give us the cheats regarding like the consistency of the linear terms and the quadratic terms, or there is no solution, and then, you know, it won't satisfy. So in either case, either it won't satisfy the linear, the quadratic equation, or it wouldn't satisfy the tensor structure. One of them has to be here. And that's the whole thing. And that's the linear PCP for quadratic equations. And before I pause for questions, just to say what we're going to do in the next 5 to 10 minutes is just to show how we can use the linearity testing that we had before in order to remove this annoying linearity constraint and talk about, you know, a bona fide PCP. Any questions? Okay, so let's see if anyone has an idea on how to transform a linear PCP to a PCP. Well, the trick is obviously using the Hadamard test. So maybe before I see your ideas, let me just say what we'll try to prove. and what's the most naive thing which definitely fails. So, you know, it's a long equation, but it's really just like to track things. So we color coded it. So I'm starting with some linear PCP. And there is completeness and soundness. So completeness will stay the same. The alphabet size will stay the same. So what's different? So in terms of soundness, the probability that we'll, you know, accidentally accept a false statement, well, it kind of remains the same, but it gets a little bit larger by a factor of 1/100. And also we have this like maximum, we'll cap it, like the probability wouldn't be too good. Fine. Of course, we can always boost it further, but think about it as like the same up to some constant. Okay, the length would get exponential. And the reason why it will get exponential, just because before we assumed that we can, you know, magically perform linear combinations, and now we'll have to literally write down the value for each one of these linear combinations. The query complexity will, you know, pick a log factor, and we'll need to have this tiny bit more randomness. So that's what we're going to show. And, you know, this, in some sense, what it would make us able to transition from linear queries to point queries. So we don't need to make any more, you know, random linear combination which access lots of points. We'll be able to make, you know, just the thing, and we'll preserve the query complexity at the cost of this exponential blowing. Okay, so this is exactly good for what we want, because we showed that we have this, you know, for any problem in NP, it admits a linear PCP with constant queries and polynomial length. And then when we apply this lemma, we get that every language in PCP, in NP, has a PCP with of 1 queries and exponential length, which was the goal that we had to begin with. Okay, soundness, we can always get it, you know, to our favorite constant just by repeating the test. So now let's just prove this lemma. So, you know, the first attempt would be to prove this lemma is the completely naive thing. So what is a completely naive thing? We start with some linear PCP and we want to construct a real PCP. So here's what we can do. Maybe what would be the proof string? Just compute the proof string for the linear PCP and provide an evaluation of it at all linear combinations, right? So this is, in other words, take your proof for the linear PCP and encode it with the Hadamard code. So for any, you know, so provide, like, take this pi and provide, literally write down an exponential list of all inner products of pi with all possible vectors in FL. Okay, so this is like an exponential blow. And then the PCP would just emulate by answering, you know, with respect to that. So just like, you know, whenever it would want to make a linear combination, it would just read the point which corresponds to that. You know, completeness would definitely hold in this case, because if you write everything exactly according to plan, then you know, you want to know a certain linear combination, then check it. But in terms of soundness, can anyone tell me what will break? If the prover just like writes down all of the values of the, like.
Again, consistency, but if we do a linearity test, then it should work, no?
Exactly. So you have both the problem and the solution, but not all of it. So what do I mean by that? So the problem is that, who knows, like the prover might write that this is the inner product of pi with A, but maybe it's not. And maybe, you know, for each different pi, it gives me, you know, for each location, it will give me a different pi. And I don't know, like, anything regarding the reliability of this thing. So we need to check that the function is actually a linear function. We need to check that this pi that is sending, the big pi, is actually consisting of all of the linear combinations, all of these linear combinations. Okay, good. So in other words, which set of functions are exactly of this form? The set of all linear functions. So what I want to do is I want to know whether a function is a linear function or not. And for that, we have the linearity testing. So what would be the second attempt for that? We'll start with the PCP. And that's kind of like, it's exactly what Shafiq suggested. So the prover will be exactly the same as before, only now we'll check that, that whatever the prover sent us is actually past the BLR test, past our linearity test. And then we can kind of, just simulate the linear PCP because we tested that the oracle is really linear. So this almost works. So of course, as before, completeness will hold, because if the prover is sending a linear function, obviously the linearity test will accept with probability 1. This is what we've shown. But the point is that if the input is a bad input, it's not in the language, then, and we get this, malicious proof, some proof we try to convince us nonetheless, then there are two cases. We fix some constant threshold, it doesn't really matter what. So either the proof is really far from being linear, or it is really close to being linear, right? If it is very far from being linear, then the linearity test would say, well, this is very far. Well, because remember that what we had, it's a property testing algorithm, so we accept linear and we reject things which are far from linear. But if we are close to being linear, but not linear, then in fact, we don't know, right? So this is kind of a problem. So the question is, what do we do in this case? So let me illustrate the problem a little better. So, suppose that we are somewhere in this gray zone, and we are close to being linear, but we're not quite linear. So let's denote by pi corrected, pi hat, the actual linear proof, the actual linear function which is closest to the function that we have. Okay. So, this is unique because it's like 1/8 closed, and then the distance is like really, really, really high. So it's definitely within the unique decoding radius. There is a unique linear function to which we'll close by the property of the Hadamard code. And then what's happening in soundness? So the probability that we'll accept this false proof, it can be split into two different cases. One is probability that we'll accept, given that all of the queries that we've made are in which the real function, the real linear function, and the noisy function agree. If this is the case, then this is exactly as we had before. So I'm saying, what happened if we're making now this O of 1 queries, and if this O of 1 queries actually happen to fall on the places where the function is really linear. So in which case, we're good. But there is also this probability that we made at least one query where it's noisy. Well, it's not really as in the linear function. And then what do we do with that? So notice that what I'd like to write here, but it's not really the case, is that I want to say, this is the soundness of in the case where we actually get the real proof, because it happened to be that we only queried places where we agree with the real proof. But the problem is that if you look at this, we make Q queries, and this is like the chance, the fractional distance. So this is like the probability of us hitting where these two, a noisy element, where these two proofs disagree. And the point is that this can only hold if the queries that we're making are completely uniform at random. So just to make this really simple thing less confusing. So suppose that you had this proof, purported proof by tilde. If this thing is very far from a linear function, then we'll reject by the BLR test. We'll reject by the linearity test. If not, it means that there is only a small number of places where there is error. And now what I want to say, what is the probability that I will succeed in my test? So if it happens to be the case that I just query the good places where there is no corruption, then obviously I will succeed because it's as before. And then I'm saying, what is the probability of me hitting a bad point? Well, it's this 1/8 that we have times the number of queries. But the point is that the queries that we're making are not independent. They are very structured. And in fact, what we actually do is structured. And so we can't make these things. So I need to have some tool in which, I want to query this red point, but I can't because it's corrupted. So how do I correct the value? Can anyone?
We make them, yeah, I think we can make them independent because we can use the fact that it's a linear function. So instead of querying at the point that we want to query, we query like at that point plus y and at y, and then we subtract them.
Absolutely. So just to kind of like take traffic series and make it more explicit. So, I have this like big linear function. And let's say that I have this one bad point x, and I want to get the function here. So we can use our old triangle friend, right? And pick the bad point x, a random point r, and then x plus r. So now these points, because they're random, with a good probability they won't be corrupted. I hit a point here, this would be maybe r, and this would be x plus r. But using that, I can extract the value that I care. So I can emulate these non-random queries by a random query. And that's exactly the last thing that we'll do today.
I have a question. Why do you say that the queries in our LPCP are not random to begin with?
Not the queries of LPCP are not random, but the LPCP that we constructed, in which case it's like there is correlations, because and why there are correlations? Because we do consistency check. So suppose I want to, I want to query this term, quadratic term x1 times x7. So it means that I will actually query the linear term x1 times x7. I'm not just like probing completely random points in the PCP, in the particular PCP that we constructed.
Okay, so the non-random part is coming from the quadratic check, not the linear check that we saw earlier, right?
Yes, it comes exactly from this consistency check between the linear part and the quadratic part.
Got it. Yes. Okay.
But I think in our construction, every query is uniformly distributed, right? If considered separately, just third query. No. This quadratic query is not uniform.
Yeah, it's not uniform exactly because we need to check this consistency. Now, if you want an exercise or something nice to think about, you can ask yourself, could it be the case that I'll get a non-trivial PCP in which the queries are completely uniform at random? That's an interesting question to think about. I mean, is this a coincidence that I'm so confidently saying that what we did is not like that the queries are correlated or not? But I leave you kind of like to think about it as a food for thought. So just to finish the last thing that I want to say today, it will take 2 minutes. Okay. So let's see. So we have what we'll do is the PCP would be exactly as before. We'll just take the function, encode it by Hadamard, or alternatively provide its all of its linear combinations, and then we'll have a verifier, and the verifier will first run the linearity test, and then we'll simulate the linear PCP simply by replacing each vector by the plurality vote, by some, what we'll do some random sampling, we'll check a bunch of triangles, we'll see which value is most popular, and we'll answer according to that. And now, as for the soundness, I mean, we have it all written here, so it would be, nice and clear, but essentially both completeness and soundness just follow by, completeness follows because if everything is according to plan, like then the linearity just would follow, and then the plurality vote would always give you what you'd expect. And soundness, we'll keep having these two cases. One of them, well, the proof is far from being linear, in which case we'll reject. The other case, we're close to linear, and then using the self-correction, we'll actually get with high probability the non-corrupted values, so we can emulate an access to the real low degree, to the real linear function, and then we'll accept according to the linear PCP. Okay, so this is all I wanted to say here. You have the details on the slide, just so we can double check, but it's exactly this thing that we said. Okay, so at this point I'll stop the recording.